at the end of the last class, I set you an exercise, and the exercise was that you were to use squared paper or graph paper in order to work out the area of your hand. Okay, and what you were to do was you were to basically sketch an outline of your hand over graph paper. Then you were to count all the squares that were fully covered, and then you were to count any square that was over half covered. Okay, so you had to use your judgment on whether a square would be included or excluded from your area. So just to make sure we all understand how to do that, take for example this irregular shape. Now, the reason why this shape is called irregular is because it doesn't fit any of the regular shapes that we know. It's not a circle, it's not a triangle, it's not a rectangle. Okay, so therefore if it doesn't fall into one of those three, we simply call it irregular. And say for example somebody said to me, well, estimate the area of this irregular shape. What would I do? Well, the first time is I would draw an outline of the shape, as you can see there, and then I would start to tick off the boxes that are fully filled. So first of all, that one, this one, this one, this one, this one. I'm just going to do this very quickly. The fully filled ones first, and then we'll go to the ones where we have to think about it. Okay, now let's go around the outside. I'm not going to tick that because that is less than half, but I am going to tick this one. That's more than half, that's more than half, that's not. This one here is more than half, that's not more than half, that is, that is, that is, that's not. This one here is, this one here is, this one here is, and finally this one here is over half full. So in order to approximate the area, we would simply say that the approximate area is equal to how many squares altogether? Well, we can see from here because I have them already numbered. It would be 38 units squared. Now, the reason why I'm saying unit squared is because we're not too sure what measurement the squares have. Okay, I think in most of your graph paper that you were using, your squares were 1 centimeter by 1 centimeter. But if they're not, and you're not too sure what size they are, just count the squares that are fully filled, count the squares that are over half filled, and then call the result units squared. Okay, and that just means we're not too sure what the squares are, but we'll call them units squared instead, and that's perfectly fine. That's an acceptable way to approximate the measurement. Okay, so I'm going to ask you to take a look at these, and these are already in your slides, so you can do these yourselves. I'm just going to do one with you to make sure you understand exactly what we're doing. The top three are regulars, all right? Top three are triangles. The bottom three then are irregulars because they don't fit circle, triangle, or rectangle. So let me just take one of them, and I'm going to go through part 5, and I'm going to see if I can approximate what the area is for the shaded region in part 5. So what do? I draw an outline of the shape onto squared paper. I tick the squares that are fully filled first of all, like that, and then I go around the outside and I have to try and guess whether they are over half filled. Well, this one here definitely is. This one here is not. This one here is. This one here is. That is not. Well, it's kind of a half and half, isn't it really? It's interesting. Well, we say it is. Okay, this one here is definitely. This one here is exactly half. We include it, and this one here is exactly half. That's less and that's more. So if I was asked what's the approximate area, I would say the approximate area is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 units squared. Again, because I'm not too sure what the size of the squares are. If the squares were 1 centimeter by 1 centimeter, then I would say that the area would be 12 centimeters squared. So because I'm not too sure, I just call them units squared. Okay, so I'm going to leave the other 5 for you to do yourselves when you're going through the slides, just to make sure you understand exactly how to count the full squares and then the squares that are over half full. Oh yeah, by the way, look, see up here, each square is 1 centimeter squared. So therefore, I can be very certain, I can take out that units, and instead of units, I can simply say centimeters squared. I forgot that part up there. So I did say to you already, each square is a centimeter squared. Now, what's a centimeter squared? By the way, 1 centimeter squared is a square whose sides are 1 centimeter by 1 centimeter. That's what 1 centimeter squared actually means. Okay, so again, sticking with the regular shapes, the exercises I left you with was to do the area of your hand. Okay, so you were to take a bit of graph paper, you were to take your hand and a pencil, you were to draw an outline of your hand, and then you were to count the squares. Now, if you knew that the squares in your copy were 1 centimeter by 1 centimeter, then you could say the number of squares in centimeters squared. If you're not too sure, just say units squared. Okay, and again, that was an exercise that I asked you to upload to the classwork section of Google Classroom, and I'll have a look and send you back the results as soon as I have corrected them. Okay, so that's what we were doing there. Now, I want to move on to 3D objects because you're going to get another exercise from me today, which is to be done in the kitchen. And 3D objects are what they say. They're three-dimensional. Now, what's the difference between 2D and 3D? The answer is 2D is always flat, whereas three-dimensional has length as well as width as well as height. So it has volume, okay? So there's the difference between them. So 2D means a flat shape like a sheet of paper, whereas 3D would have volume. So if I was to take a sheet of paper on a desk like that, there it is. Now, if I was to take that sheet of paper like this, and if I was to give that sheet of paper some height, see, straight away it begins to look like a box. And that's exactly what it is, because if I join those, then I get volume. So that would be a 3D object, whereas that one there would be a 2D object, just in case you're not too sure what 3D and 2D mean. So what I want to try and do now is I want to measure the surface of the area of the 3D object. Now, I want you to think for a moment of a rectangular box, okay? So if we think of a rectangular box like this, let's just put down a rectangular box on the bottom here like that. Give it a bit of height, 1, 2, 3, and 4, and finish these off. Okay, what do I notice about this 3D object? The first thing I notice is that its surface is made up of rectangles, okay? The first rectangle is here on the right hand side, but that is matched by the one that's on the left hand side. Then we have one that's on the top, but that's matched by the one that is at the bottom. Then we have one in front and one at the back, which we'll call number 6 in there. So there are 6 faces to this, okay? And the lovely thing is that they are 6 rectangles. So what I could say is I could call this here the right hand side, I could call this one here the top, and I could call this one here the front, okay? So let me just do that again. Let's just take out what I've written in there already. Let's take out the 6, let's take out the R, take out the 4, the F, and the 2. Now I'm just going to break it down to 3 this time. So we have the top, we have the right hand face, and we have the front, okay? The front and the back are exactly the same. So front is equal to the back, the right is equal to the left, and the top is equal to the bottom. So therefore what I could say is that the surface area would be 2 times the front, plus 2 times the right face, plus 2 times the top, okay? And that added together would give you the total surface area of this particular 3-dimensional object. Now, to make it a little bit easier to see, all 3D objects have what are called, and you may have done this already in maths, you may have done it in 6th class or 5th class, all 3D objects have what is called a 2-dimensional or a flat net shape, okay? So take this thing here, take the rectangular box, and let's say we were to open it fully and turn it into a flat 2D shape. What would we get? Well, there's my rectangular box there, and if I was to open it flat, I'd get the following. Now notice what I said. There's the bottom, there's the top, yeah, there's the right, there's the left, and there's the front, and there's the back. So what did we say? If you have right and left, 2 times right, because they're the same, so you can put that into R as well, so it's 2 rights. You could say this is the back as well, so 2 backs, and then you could say that the bottom and the top are the same, okay? So bottom and top are the same, the left and the right are the same, and the front and the back are the same. So it's kind of easy enough to calculate when you're dealing with something like that. Okay, so that's your net, and a net is the 2-dimensional object, or 2-dimensional, I should say, representation of a 3-dimensional object. So the flattened 2D shape of any 3-dimensional object is called a net, and the net is used because it helps me to calculate the surface area, okay? So using nets helps us to calculate the surface area of a more complex 3D object. Now I want you in your own time, when you get these slides in Google Classroom, I want you to click on that and take a look at how we make nets of 3-dimensional objects. And this is a lovely website, because what it does is it gives you all the 3-dimensional objects, and by pulling a lever they open up into their flat 2D net representation. So make sure you take a look at that link before you move on and look at the rest of these particular slides. So even if you want to pause now, go to the slides, click on the link, have a look at the nets so you can come back and understand exactly what I'm talking about. So I'm going to leave you with an exercise here on this slide, and that is to try and figure out, you can research this, so you can use Google or use your maths book, or you can use your science book, whatever you want to do. how could you work out the surface area of all of these 3D shapes? So how do I get the surface area of a cube, a rectangle, a cylinder, a cone, and a sphere? All right. So I want you to look up, research, Google, or research your maths book or your science book, and come back to me with an exercise written out. You're going to upload this into the classwork section as well, as to how I would work out the total surface area. Now, you may find that there's a formula given. If you can discover a formula, then I would ask you to write it down and put that in as well. They might give you a net. I would ask you to draw that if you can find it, see what the net would look like, and then you can upload that as well by taking a photograph of your work. So I'm going to leave that little bit of research to you, and we're going to move on. Now, volume. Remember I told you already, if this thing here is flat, see that? And if I give it height, like this, then all of a sudden, my shape now has volume. So how do I define volume from the point of view of science? Volume is found in any object that takes up space. Now, does a flat piece of paper take up space? No. Does it take up area? Yes. Does a rectangular box that your shoes or new runners come in, does that take up space? Yes. Does the bench in the middle of your kitchen take up space? Yes. Does the table in your dining room take up space? Does the couch take up space? Yeah. So anything that takes up space is a three-dimensional object. And if it's a 3D object, it has volume. All right. So the one thing I want you to remember is the word volume. If anybody asks you, what does volume mean? You can simply tell them volume is found in anything that takes up space. All right. And I've gone through a couple of examples there for you already. So we're going to try and figure out, how do I measure the volume of three-dimensional objects? So as well as having length, as we said, and width, 3D objects also have height. And it's even the same for triangles. So if I was to draw a flat triangle like this, right, that has area. But if I was to give it height like this, you see what happened? Straight away, it turns into a three-dimensional object. And now it takes up area. So it's like a bit of cheese. Yeah, a bit of Swiss cheese there like that. So you see, I started off with a flat triangle and I gave it height, and all of a sudden it becomes a three-dimensional object. So as well as having width and length in their area, they also have height, or what we could call depth. Now, take it this way. There's your triangle, and let's give it a bit of depth this way. And what have I got? I've got my Toblerone. See? I've got a box that holds my lovely favourite chocolate, Toblerone. So that's what three-dimensional objects actually are. So when we talk about height or depth, we talk about height as going upwards and depth as going back into a page or back into the whiteboard that we're working on. Okay, so there's an example of your length, your width, and your height. Now, length and width give area, but once you give the area height, you turn into three-dimensional object. Take a coin. If you put a coin on the table, that's what it looks like, okay? But as soon as you give the coin a little bit of height, it becomes an object. If you give it a lot of height, it becomes a cylinder. Okay, so there's your coin, and there's the markings on the edge there, and this is a €2 coin that way. All right, but if it was a flat piece of paper, it wouldn't be taking up any space. So a circle with height becomes a cylinder, a rectangle with height becomes a cuboid, a triangle with height becomes a prism, and so on. So there are special names that I'm going to leave for your maths teachers to deal with. We don't really have to worry about that just yet. We have to worry about anything that has width and length and also height has three-dimensional volume. Any object that takes up space has volume. Now, I've told you that before. That's the definition. Volume is found in any object that takes up space. So rectangular boxes have regular volumes, but objects like stones would have irregular volumes. So what does that mean? To have a regular volume, the size of the object, the sides of the object must be measurable. Okay, now let's go up here. Let's take this rectangular box. This rectangular box has a regular volume. What does that mean? Well, maybe the length of it is 7 centimeters. Maybe the width of it is 5 centimeters. And maybe the height is 4 centimeters. Now, if that was the case, that would give me a regular volume because the sides are measurable. All right, we can use a ruler to measure them straight away. And I think you know for your maths already, 7 5s are 35. And then we have 35 times 4, which is 140 centimeters cubed. So that would be the total volume or the total size. I suppose another word for volume is size. That's another way to describe volume. anything that has size, yeah, is volume. Okay, so if I want to get the volume of that box, it's the length, 7, multiplied by the width, 5, multiplied by the height, 4, which is 140 centimeters cubed. Okay, so what about let's stick with the regular volumes for a while. To get the area of a rectangular box, we measure the length, then we measure the width, we measure the height. So you've got to get 3 measurements: length, width, and height. And we do that by using a ruler. Okay, so we're back to the very beginning of this chapter. An ordinary instrument to measure length and width and height is the ruler. You write down what the length is, you write down the width and the height, and you multiply them together, which means if you're multiplying 3 things together, well, then you're going to end up getting an object in centimeters cubed. Now, I want you to stop for a moment. Length is in centimeters, okay? Area is in centimeters squared because we multiply 2 things, length by width. So therefore, volume, if you're multiplying length by width by height, must be in centimeters cubed. So you'll notice the more times we multiply, the higher the power gets over the centimeters. So what would the volume of this box here be? Well, 10 fours are 40, and 40 times 5 is 200 units cubed. And the reason why it's cubed is because you're multiplying 3 numbers together to get the volume. Okay, so length by width by height gives you the volume of the box. And if you're told what the units are, say for example we were told that this was 10 millimeters, and this was 4 millimeters, and this was 5 millimeters, well then we know that straight away this would be not units cubed but millimeters cubed, see? And if that was centimeters and centimeters and centimeters, then it would be centimeters cubed. So you've got to be very careful to make sure that when you're multiplying out the volume of a rectangular box, that you look to see what units am I measuring in. And whatever unit you're measuring the length and the width and the height in, they will be the same units that you'll have in your volume, except they'll be cubed at the end, because it's important to be accurate and important to give back the correct measurements. Okay, but what about irregulars? What about if I gave you a big stone like this? Yeah, say I gave you a big stone. There's your stone there like that. And that's a big lump of concrete. What formula do I use to get the volume of that thing? Well, is there half a base by the perpendicular, height by the width? No. Is it length by breadth by width? No. Do I use an opposometer? No. How am I going to do this? If it's not regular, then we have a huge mathematical problem. Because if it's irregular, then we can't use any standard equipment to measure. We can't use the ruler, we can't use the opposometer, we can't measure volume using any of the instruments we've already met. But there's a cheap way, and there's a very clever way to do this, and this goes back to what we call the principle of Archimedes. Now, if you have never heard of the principle of Archimedes, I want you, when you go to the slides, to watch that video, okay? Because that video will tell you exactly where the principle of Archimedes came from. But basically, in a nutshell, the principle of Archimedes is this. If you put an object that has volume into water, the object will push out its own volume, so the water will rise. Now, a typical example would be the following. Say you fill the bath right up to the very brim, okay? And it wasn't spilling over, but it was right up to the very top. As soon as you go to get in, the water is going to start pouring out the edges. Why? Because your body has volume, and your body is going to push out a volume of water that is equal to your size. And this is what Archimedes found out. Okay, and you can look at the story yourself. But he discovered that whenever you submerge anything in water that has volume, the amount of water that comes out is exactly the same size as the object that you put into the water. Hey presto, problem solved. All we have to do now is to find an object in the lab that is extremely accurate for measuring volumes of water. It's not a beaker, it's not a conical flask, but it's a graduated cylinder. And the graduated cylinder, as we're going to meet now in a moment, is what we are going to use to help us to get the volume of any irregular object, thanks to the principle of Archimedes. Okay, now could I use a beaker? Well, would a beaker give me an accurate answer? No, a beaker would give me an approximate answer. So just to demonstrate here quickly, if I take this stone here and I put that stone into 30 centimeters cubed of water, and when I submerge the stone, I see that the water has gone up by it's gone up to 46 centimeters cubed. Does that mean I have created water? No. What had happened is that the stone has pushed out its own size. So the water has risen to exactly the same size as the stone. So if the water was 30 and then the water went up to 46, that's a difference of 16 centimeters cubed. So now I know that the approximate volume of the stone is 16 centimeters cubed. That's called displacement, okay? It's called, there's the word there, it's called displacement. So the stone goes into the water is displaced upwards, the new reading is taken, and you see the reading that you started with before you submerged the stone, you see the volume that you end with after you submerged the stone, and you take the two away from each other, and all you can say is, well, the reason why the water went up is because I put the stone in. So the stone is responsible for the rise in water, and the volume of the rise is the same as the volume of the stone. Now, we could use a beaker if we didn't want to be if we wanted to be approximate, then a beaker would be okay. But scientists, I told you at the start of this thing, when we're measuring, we have to be accurate. So we're going to move to the graduated cylinder, okay? Now, we've used these before, and you see on this thing here that there are lovely measurements from 50 all the way up to 500. So they're fairly big, decent pieces of glassware, okay? And you've got to be careful handling because they smash easy. So let's say, for example, that I was to start off at 150, okay? Now I'm going to show you, see the way I drew a U-shape there? I'm going to talk more about it later on. Because when water goes into anything that's glass, it forms a U-shape. But we have to measure from the middle. We have to measure from here. And I'm going to talk more about that later on. So this would be 150 centimeters cubed. See that? You don't read from the sides because glass pulls water upwards. So that's false. That's a false reading and that's a false reading. So we only read from the bottom. And let's say, for example, then that I put in a block. Let's just say I put in a block. Okay, like that. And the block fell to the bottom and the water went up to here. Now, what would you say? Well, it was 150. It is now 200. So therefore, the difference between them is 50, meaning that this block had a volume of 50 centimeters cubed. And the lovely thing about graduated cylinders is that they measure in milliliters. See that? And milliliters are exactly the same as centimeters cubed. They're the same thing. So milliliters are the same as centimeters cubed. So when you see milliliters up there, remember that milliliters also mean centimeters cubed. Okay, so let's just take that away. Now, let's take a look at this. The graduated cylinder is when we want to be accurate, and that's the key thing. If we want to accurately measure volume, we use the graduated cylinder. If I'm not too pushed and I want to be sloppy in my work and I want to give approximate answers, by all means use a beaker. But a beaker was never designed to measure water. A beaker was only ever designed to hold water of an approximate volume, okay? So we would never contemplate using a beaker if we wanted to do things accurately. We'd always use the graduated cylinder. It has centimeters cubed on its side. Now you'll notice it says mils, but mils are centimeters cubed, so they're the same thing. It's just a different name for exactly the same unit. And we have to be careful. A beaker should never be used if we want to be accurate, because beakers only give approximate volumes, okay? So it must be the graduated cylinder. Now let's take an example. If the stone is small enough to fit into the graduated cylinder, we will simply place a known volume of water into the graduated cylinder and immerse the stone carefully into the water. So let's take a look. Now, take this example here. I start off with 90 centimeters cubed. I immerse the stone and it goes up to 130. What was 90 goes to 130. Now, who's responsible for pushing the water upwards? The stone is. And the stone pushes out its own size, its own volume. So that means that the stone has caused an increase of 40 centimeters cubed. So I can easily say now that the stone has a volume of 40 centimeters cubed. It's a lovely way to get around the problem of not having a formula to calculate the volume of an irregular object. Okay, so the rise in water represents the volume of the stone. And what's the volume of the stone used here? Well, the water was at 90. After the stone is submerged, it goes up to 130. The difference between the two is exactly the same size as the object, the stone in this case here. So the answer is 40 centimeters cubed. Now, this is what I spoke about earlier on. When you are measuring from the graduated cylinder, when you're reading from the graduated cylinder, you have to read from the bottom of this U-shape. Do you see that? Because when you put water into any glass object, it kind of goes into a U-shape. Yeah, the glass pulls the water upwards. So The edges would never give you the true reading. The true reading is always taken from the center. So we take a look here at this U shape, and by the way, the little U shape, the boundary of the liquid there that's in a U shape is called a meniscus. That's an important word, okay? So the meniscus here, we measure from the bottom of it, and you can see it from there. So we measure from here. So we have to be very careful that we hold the graduated cylinder up at eye level. And by holding it at eye level, we look for the bottom of that little U-shaped meniscus, and wherever the U shape is, that's where we measure from. So let's take a look here. What have we got? We've got 20 and 21. All right, so this is 21 here. Now, take a look. The bottom of the U shape is between 20 and 21, and it kind of looks as if it's about halfway. So I would be quite happy to say that the volume of liquid in there is 20.5. Yeah? 20, am I writing that? Oh, sorry, my mistake. Down here, I have it written out. Let's go back there again. Okay, so there's 20. Pen. So that's 20. Sorry, that line there is 20. So that's 20, 21, and 22. So that's 21, that's 20, and that's 22. So now, what do I notice? The bottom of the meniscus, you have to remember that word, there it is. That's the bottom of the U shape, is halfway between 21 and 22. So I'm quite happy to say that the volume of water in that graduated cylinder is 21.5 centimeters cubed. Now notice, we don't have any smaller units between the 21 and 22, so you kind of have to guess. But it's okay, because it is fairly accurate if you give 21.5 as the volume in that graduated cylinder. Okay, so I want you to take a look at this, and I want you to ask yourself a question. What's the volume of water in these two graduated cylinders? Well, let's take the first one. Now you can pause your video now, and try and come up with the answers yourselves before I give you the answer. Okay, let's take a look. What have we got? We've got 20 and 30. We've got 10 units. So every single one of these units here is 1 centimeter cubed. Now, we don't measure from the edge, and we don't measure from the edge. We only measure from the middle of the meniscus. So therefore, the middle of the meniscus is on that line, which happens to be 1, 2, 3, 4 units above 20. So therefore, this is 24 centimeters cubed. See that? 24 centimeters cubed. Okay, what about this one? We don't measure from the edge. We go from the middle of the meniscus. 2 M's. Middle meniscus. Keep the M's together. Middle meniscus. What's this going to be? Well, 6 up to 7. Now be careful. There are 10 units between 6 and 7 here, so each one of those little lines must be 0.1. 6.1, 6.2, 6.3, 6.4, 6.5, 6.6 centimeters cubed. Okay, so quite a relatively easy thing to do, as long as you're careful to measure from the middle of the meniscus. So please remember that. Measure from the middle of the meniscus. Okay, what about these? Now I'm going to leave these as an exercise for you to do, and I want you, in the homework that you're going to do for me, to write down what volume of water is present in each one of these graduated cylinders. Okay, so that's part 1, part 2, part 3, I've got to label these, part 4, part 5, part 6, part 7, and part 8. So if you can manage them, then you're a genius reading a graduated cylinder, and that's exactly what we need to do, because we need to be accurate. So just keep in mind, please measure from the middle of the meniscus. The middle, I'm going to put down here again, middle of the meniscus. Okay, so you can pause now, go along, work out the volumes in each one of those 8 graduated cylinders, write them down, and when you're sending back a photograph of your homework to me, we'll check them and I'll send them back to you, or else we'll do them in the live class when we have live class at the end of this week on Thursday. Okay, so what's the volume of the irregular object shown here? Now this is, again, quite easy to do. What are we dealing with? We're starting here with 600. We put in the object and it rises to 800, which means the difference between the two is 200, and that difference is the volume of the object that is present. So that's the principle of Archimedes, and that's how we work out accurately the volume of an irregular solid. Use a graduated cylinder, use an object that can sink, Okay, make sure it can sink, or if it can't sink, submerge it in some way. You don't use your finger, it's too big, but use a pin or something to push it under the surface. Okay, if it was a cork, for example, you could stick a pin into a cork and you could push the cork under the surface. The pin is too small to make any difference, and you can get your volume that way. But you take the reading before you submerge the object, you take the reading after you submerge the object, and you take the two away in order to give you the volume of the object that has displaced its own size. Okay, again, another object for you, another exercise for you to do. All of these start at what? Well, where are we? They start at 15, 16, they start at 17. When you put a battery in, what does it go up to? And what's the volume of the battery? What's the volume of the nail? What's the volume of the button? What's the volume of the key? That's for you to work out. And I want you to work out these four by using Archimedes' principle, which simply means put the object in, see where the water was at the beginning, and all of them started here. This is the start for all of them. What do they end up with? Subtract the two, and that's the volume of the object that is present in each one. So again, there's another exercise for you to do, for you to send back to me in Google Classroom. Okay, so finally, if the object is too large, so say for example, I get the biggest graduated cylinder I have, but the object still won't fit. So say for example a potato. Potato's not going to fit into a graduated cylinder, it's too big. Okay, so what do? I still have to use the principle of Archimedes. I still have to use the graduated cylinder, because the graduated cylinder is the only accurate way we have of measuring volumes of water. But I have to get another way to displace the water by the big object. And what we do is we bring in another piece of equipment. And this piece of equipment is called an overflow can. Now, what does an overflow can look like? Well, there it is. It looks like a beaker, but it has a spout. Okay, and what you do is you fill the overflow can right up to the spout itself. Allow it to settle. Then you dump your object in like this, and watch what happens. Splash. There it goes. What's happened? Oh, look. We've got water in here. But the water in here has to have exactly the same size as the object, because don't forget the principle of Archimedes. Every object pushes out its own volume. So if you put the big potato in here like that, then out of the spout is going to come the water that is pushed out by the potato, and that has to have exactly the same volume as the potato. So can I measure it? Yes, I can. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 105. So that is 105 centimeters cubed, and the graduated cylinder doesn't lie. So again, measuring from the middle, we can't really see a meniscus here, but if we was there, we'd measure it from the middle. Okay, good. Now, what's the object of this volume? So again, we've taken a big potato, we've put the potato into water, or a big large rock. We've allowed the overflow can to settle, so you have to give it a while to make sure the water stops flowing out the spout. But when we put the object in, it pushes out its own volume this way, and when it settles, we read from the bottom of the meniscus. Do you see that? Now, what can I see here? Well, every unit is 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Ah, that is 14 centimeters cubed. Whoops, excuse me. 14 centimeters cubed. Okay, now I'm going to stop there because I've done a lot of exercise with you, but the three things I want you to remember from this class are as follows. If I want to get the volume of a regular shape, then I have to use a formula. The volume of a regular box, length by width by height. Okay. If I want to get the volume of an irregular thing like a stone or a potato or something that has an unusual shape, then I either use the graduated cylinder on its own if the object is small enough to fit in. I put in a certain amount of water that I can read. Then I put in the object. I see by how much the water is pushed upwards, and the difference in where I started and where I finished is exactly the same as the size of the object. If the object doesn't fit, well then we have to use an overflow can. This thing here, this is the overflow can, and it's named that for a very important reason, that the water overflows when you put it in. And because of the principle of Archimedes, this object pushes out its own size, and it all flows out here into this graduated cylinder, and we still use the graduated cylinder in order to be accurate about the volume of water that is present in the graduated cylinder. So the volume of water that's here. Yeah, and we can see from the bottom of the meniscus that is 14 centimeters cubed. Okay, There is a practical for you to do in Google Classroom, which I'm going to ask you to do on Tuesday for the time that we normally have science, and it involves a very, very simple way of using household equipment like kitchen utensils to measure the volume of an object. So you can go to Google Classroom, go into the classwork section, look at the little practical that I've set for you, do it. If you want to video yourself doing it, that would be much better. You can video the practical, put it up into the classwork section, then go over the slides and answer the questions in terms of the volume in the graduated cylinders and being able to read the meniscus from the bottom. But do the exercises from the slides, do the practical in the classwork section, send up your videos to the classwork section, take a photograph of your written work and send that up with it. And I'll come back to you then for another lecture on Wednesday and a live class on Thursday where we'll go through the answers and the videos of your practical.